So welcome back. Okay. So what we are looking at are basic tenets of special theory of relativity. Of course, special theory of relativity is a prerequisite for this course. So we are just going to use this review to basically introduce the notation. So that is a basic idea. So we are going to do a very fast review of special theory of relativity. While introducing the notation what we want essentially. So what we did was we introduced the notation of x mu, which is in Einstein's frame essentially where 0 1 2 3 our 1 2 3 indices are the space indices and 0 is the time index. And then we said that in Galilei transformations the length of the vector does not change, whereas in special theory of relativity the length of the vector is no longer a constant, it does change. So what you do is you have something called line element which is invariant. So the line element is invariant in special theory of relativity. Okay, in special theory of relativity this is invariant. Now so now how do you make sure that this is invariant? Okay, other thing before going to that I introduce you a metric tensor with minus sign on the on the time axis essentially. There is also another possibility, other possibility of the metric tensor is 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. Okay. This is also another choice for the metric tensor. In this case what happens, ds square is equal to okay, c square t square. Now c square t square is times minus x square minus y square minus z square essentially. This is the definition. So x mu would be t c t minus x minus y minus z, whereas x mu upper indices would be c t x mu x y z without the minus signs. Now I also introduced you something called the natural units. I will go a little bit more on this because this is very crucial because I will be using a lot this one. I cursorily mentioned it in here. So what are natural units? Natural units, because in non-relativistic quantum mechanics review I put explicitly h cross everywhere essentially just to see what it is, just to show where the h cross will appear. Similarly you can do the same thing in special theory of relativity where c appears naturally essentially. But in we move to relativistic regime and studying quantum mechanics in that essentially it is much more fun to use something called natural units, in which what we set is h cross is equal to 1 and c is equal to 1. So now remember that h cross and c both are dimensionful parameters essentially, they are both dimensionful parameters. H cross contains angular momentum dimensions, whereas c contains velocity dimensions. So the consequence of setting h cross and c is equal to 1 are essentially that you start measuring things, everything in terms of energy units essentially. Length will be measured in energy units. Okay. Similarly, time will also be in energy units. So, everything mass will also be measured So, for example, if you say what is the mass of a proton, okay, mass of a proton is equal to 1 GeV, okay. You instead of saying this many kg or something, essentially you say it is to be 1 GeV essentially. Okay. Similarly, what is the, so if you have a length scale, this will be measured in MeV inverse or GeV inverse units. Okay. So, if there is a length scale associated, essentially time periods will also be measured in MeV inverse or GeV inverse units. You will be using these particular units, these are called natural units. So, this you can always go back to SI units by appropriate substitution of H cross and C. Okay. You can always put H cross and C correspondingly, and then you get your corresponding time units essentially, or whatever SI units the measurement you have done essentially. Okay. Now, I will not be using all through natural units, there will be some places where I need the H cross and C, for example. Okay. In those cases I will be telling you where I am putting explicitly and what happens the case when I do not put, what happens to the case when it is natural units essentially. Okay. So, there are several what happens to, so you can, so there is an exercise assignment problem essentially where you convert many many well known objects in terms of natural units essentially. So, many well known things essentially you will be converting into natural units. So, before going further, I just want to introduce you one more thing which is, so the one tensor which you have seen is the metric tensor, which essentially is a unit matrix with minus signs essentially. So, this defines for, this is important for you to define the minus signs. Then I will also introduce you Lorentz transformations. And the way I am doing it is the one, so such that I will use it later on to define the Lorentz group, that is the reason why I am introducing you in this particular fashion. So, I will define the Lorentz group later on, but here I will just set the notation because today is only the notation day. Okay. So, the what are Lorentz transformations? So, just like Lorentz transformation are combination of rotation and boost. Boost are essentially like Galilean transformations, but with speeds closer to the speed of light essentially. Okay. So, boosts are like Galilean transformations, but boosts are defined in such a way because they can contribute to increase the lifetime of a particle in a different frame of reference and also decrease the length scale of certain objects, okay, in a different frame of reference essentially. So, Lorentz transformations are a combination of boost and rotations. We will see them when we study the Poincare group in more detail and group theory of that essentially. But to set the notation, so but to just set the notation, as we said, x mu is equal to lambda mu nu x nu. This thing lambda nu is the Lorentz transformation. Okay, this is the Lorentz transformation. So, what does the Lorentz transformation conserve? What does the Lorentz transformation conserve? So, what does it keep it invariant essentially? So, what does it keep it invariant? So, it keeps, as we have seen, the line element invariant. This is the condition on a generic Lorentz transformation. Okay. This is the condition on a generic Lorentz transformation, that the line element should always be invariant. So, with this now we can introduce some notation essentially. So, we use some sort of, this is called Einstein tensor notation, Objects with no index, these are called scalars under Lorentz transformation. Objects with one index are called vectors under the same Lorentz transformations. Objects with two indices are called tensors under Lorentz transformations. So, the line element, so let us see some examples of this tensors and everything, okay, and scalars and vectors. So, an object which does not have any index is line element dx square x mu, because it is the same index which appears here and there. So, this index is summed over, this is a scalar. So, this is a Lorentz invariant scalar. Such an object is called Lorentz invariant scalar. So, in all frames of reference the scalar is the same. So, it is invariant under Lorentz transformations. So, if you move from one frame to another in the special theory of relativity, you do not use Galilean transformations, you use Lorentz transformations. So, in every frame of reference, if you want some quantity to be invariant, it to be the same, such a quantity is called a scalar. Okay. It is invariant under Lorentz transformations, such a quantity is called scalar. A quantity which transforms under Lorentz transformations, okay, is called a vector. a Lorentz vector which is x mu, okay, which is x mu. So, x mu is a Lorentz vector. Okay. Similarly, you have a mu, we will see later on we will have something called a particle which has one index which has a mu, which is also called a photon field essentially. We will see this thing later on. So, for example, this is a the a mu is nothing but the 4 vectors, every 4 vector photon, we call it as photon field, but it is also nothing but the gauge field, okay, gauge potential A and A bar, which you encounter in electrodynamics. A mu is equal to phi, this is a scalar potential and this is the vector potential. Scalar vector potential of electrodynamics and come together and form a vector essentially, and form a vector. So, it is a 4 vector and this 4 vector is also a Lorentz vector essentially, that is a basic one more example essentially. Tensor is containing 2 indices, okay, tensor contains 2 indices. Now, okay, before going to tensor, a mu transforms under Lorentz transformations. How does it transform? Just like a mu also transforms with a single a mu prime transforms in this particular fashion. So, all the vectors transform in the same fashion or in the same form under Lorentz transformations, Lorentz transformation. We will see the explicit form and the conditions on this Lorentz transformation later on, but for the present this is fine, because you all know what is the Lorentz transformation I am assuming. It is x minus v t by c and those are things essentially. Okay. So, all the vectors transform in the same fashion. So, there is an appendix here, there is an error. So, there is an appendix here. So, all the vectors transform in the same fashion under Lorentz transformations. Then what about tensors? Objects with 2 indices, these are called tensors. Okay. So, for example, you have already seen a metric tensor, metric tensor. Okay. Are there any other tensors in nature, okay, which we will use it essentially? Okay. Another famous tensor, because which we are talking about, which we will also use perhaps not very far, okay, okay, which is called the field strength tensor or F mu nu. So, F mu nu is defined in terms of del mu a nu minus del nu a mu. It is an antisymmetric product of del mu and a nu. Okay. This is also written sometimes in this fashion, antisymmetric sization in terms of the indices of mu and nu essentially, okay, in terms of indices of this thing. Now, what is del mu? What is del mu? What is del nu? This is the same del mu, F mu nu is the same thing which you see in electrodynamics. to write the covariant form of Maxwell's equations essentially F mu nu. Okay. Now what is this del nu? Del nu is also another vector, del mu is also another vector which is defined by del x mu. Okay. Del mu is also another vector which is defined as del by del x mu. So you can think it as del by del x 0, del by del x 1, del by del x 2, del by del x 3. Okay. So 4 vector essentially, it is a 4 vector. Okay. Similarly you can also have del mu which is the contravariant part of del mu essentially. So you have so whenever you see a one index 0 index object, it is invariant under Lorentz transformations. If you, and that is called a scalar. So scalars are always invariant under Lorentz transformations. Okay. And then you have vectors which transform. Okay. Under Lorentz transformations essentially. So which transform under Lorentz transformations, and then there is tensors. So I gave you examples of 2 tensors, which is the metric tensor and the other one is the field strength tensor in the electrodynamics. So there is also one more tensor, okay, there is also one more tensor which is called the energy momentum tensor, okay, T mu nu, energy momentum tensor. Which will appear in quantum field theories essentially, which appears in quantum field theories or and general theory of relativity, which we will not encounter right now. Now why is a tensor different from vector? The tensor transforms twice as much as a vector. Say for example, F mu nu prime is equal to lambda mu rho, lambda mu rho, lambda nu sigma F rho sigma. So it has 2 Lorentz transformations instead of 1 Lorentz transformation. So 2 Lorentz transformations. Okay. So we have covered sort of essentially introduced you what are the scalars, vectors and the basic foundations of special theory of relativity today. Okay. Now what it tells you is that, now we come back, one thing is that the speed of light is constant in all frames of reference, and so we set it to 1. The first one, and the second one is that all the physical laws are the same in all inertial frames of reference. That means what are laws which we derive in relativity frames should be either covariant, all the laws should be covariant or under special theory of relativity Lorentz transformations or invariant. Means what is covariant means? Covariant means they do not change the form, okay, they do not change the form under Lorentz transformations such that it should be consistent with the tenets of special theory of relativity. So the laws, the equations of motion, say for example, since we are dealing with the equations of motion, they should always be invariant, covariant under Lorentz transformations essentially. Other things, there are certain things, certain quantities which we want to be invariant under the Lorentz transformations. These are Hamiltonians essentially. The Hamiltonian is energy essentially. Energy should be a scalar. The Hamiltonian should always be a scalar under Lorentz transformation. So, it should be a invariant quantity under Lorentz transformations, whereas the equations of motion should be covariant under Lorentz transformation. So, Hamiltonian should be invariant because it is an energy. So, it is a scalar, should be a scalar. Should always be a scalar essentially. So, for the present I think this review of special theory of relativity is sufficient. Okay. This review of special theory of relativity where we introduced what are the Einstein notation and what is a vector, what is a scalar and what is a tensor under the special theory of relativity. This is sufficient. With this we will try to get head on with one of the first equations of motion. What happens if you take a non-relativistic system and just transform it into a relativistic system. So, this is what we are going to do. We will going to start with a simple energy momentum relation and then transform into a completely relativistic energy momentum relation and then see what happens, what is the equation of motion we get and what are its solutions and so on. So, okay. So, with this I will stop here essentially, and in the next class we will see the first relativistic of motion and some general features of what we expect in relativistic quantum mechanics essentially. Okay. And so, we made we have all the ingredients now to attack particles in a relativistic regime essentially. Okay. I will stop here. Okay. Thank you.